Great. Thank you, guys. Thank you. So recursion, let me create a new branch. Recursion, and let's start from here. Now let me create the Java class. I will name it basic recursion. We're going to look through 2 or 3 different recursive algorithms, probably 3 today, which are very basic coding challenges. They're not that hard. Moreover, sometimes iterative approach, which is whatever we are used to, right? Loops and iterating. So iterative approach sometimes is even more efficient than recursive, especially in today's problems. But those problems are very well descripted. So if we can look through them and understand how do they work under the hood, you understand the recursion in general. So later on, we can use it whenever it's really needed. But I'm going to show you different complexities today, and we'll see why one is more efficient than another. So first problem is, probably some of you know already, because I always use those problems for explaining recursion, and this is Fibonacci. 1 second, let me admit everybody. Great. Cool. So Fibonacci. What is Fibonacci? Fibonacci is just a series discovered by Fibonacci that looks like that. So first 2 numbers are ones, and then every next number is the sum of 2 previous. So 1, 1, 2, 3, 5, 8, 13, 21, 34, and etc. Obviously, this is infinite series, right? There is no end for that because every next number will be a sum of 2 previous. This series is very interesting in terms of where it is used in nature. So that's definitely not the topic of today's lesson, but if you're really interested, feel free to Google like Fibonacci nature or whatever, and you'll be shocked how nature uses those in different approaches. So different flowers, different so many things are built using these spirals of Fibonacci or Fibonacci sequence. Check it out. But for today, we have a next challenge. Let's say you are given with the number, let's say 5 or like 3, and you have to return the number in Fibonacci series that has this index. So 3rd number will be 2, 4th number will be 3. So you're given like index, and you have to return what is the actual number behind this index. Let's quickly do iterative approach, like easy one. So we have iterative Fibonacci, and we are given with some integer number, which is index, and we have to return integer, which is actual Fibonacci, right? So to do that, we will need to do, obviously, first 2 numbers are ones. So if somebody asks us first number or second one, this is very easy problem to return, right? Because we know exactly that first and second are ones. So basically, we need to say that if number is 1 or number is 2, then we know the result. We need to return 1. Again, I'm doing iterative approach, iterative, the one we are used to. Iterative means we can use loop, any loop to iterate. That's basically the difference. So now obviously the formula is pretty simple, right? The next one, every single number, if we are starting from third one, every single number is a sum of two previous, right? So basically, the approach number one is to store every single number in array and smoothly iterate. The approach two is store two previous numbers, and calculate every next one as a sum of two previous, right? So basically we can say that let's return Fibo1, which is 1 as by default, and Fibo2, and just Fibo, which will be, 1, 1, and just Fibo will be 1 for now. I'll explain it right now. Now, iterative approach, nothing difficult, right? We start the for loop. We start the for loop from 3 to number, including the number itself. And we are iterating, incrementing I by 1, which gives us an ability to say that every single iteration, we can say that our Fibo equals Fibo1 plus Fibo2. Same time, once we did this, we need to move Fibo1 and move Fibo2. Somebody shared the screen, sorry. Volume up, yes, I can do the volume up. Is it better now? Please use Slack, not Zoom. We don't check the Zoom chat. So please use Slack or ping me if you're not in Slack still. It is crucial to be in the Slack channel because we share all the news there. Should I do more volume up or is better? Oh, much better, thanks, cool. Great, great, great. Okay, okay. Let's do it. So Fibo is Fibo1 plus Fibo2, right? And now if we are counting third one, we say that Fibo is Fibo1 plus Fibo2. So now we need to move Fibo1 to Fibo2 and Fibo2 to Fibo, right? So just move those two. Basically, Fibo1 now is Fibo2 and Fibo2 now is Fibo. So basically, we had, this was Fibo, this was Fibo, this was Fibo1, this was Fibo2, this was Fibo. So now, before going to the next iteration of counting new Fibo, we just say that this is new Fibo1 and this is new Fibo2. In that way, we will be able to count new Fibo as a sum of those two in the next iteration. And now we just return Fibo. Should be it. Let's quickly write unit tests to make sure that everything is cool. So basic recursion test. Iterative Fibo test. So let's say I want to check out the let's say 12th Fibonacci number. And the real one is 1, 2, 3, 4, 5, 6, 7, 8, 9. Let's check it, check 9th. So let's check 9th. Number will be 9. I would create the basic recursion class here. New basic recursion. Now, I know that the actual number, result is 34. So now I can just say, sorry, this is expected result, right? Expected result, and actual result is whatever basic recursion dot iterative Fibonacci from number will give us. Now I would like to double check that those two equals expected result with actual result. That's it. Let's quickly run it. Perfect. Should be more or less trivial, right? So what are the runtime complexity and memory complexity here? Yes, so basically we have one loop. So basically big O from N is our time complexity. And we didn't use much memory, you're absolutely right. So big O from 1 is fine because we use three variables here, which is nothing, of course. Cool. Good. Now, that was our iterative approach. As I mentioned already, this is probably the most optimal one. No, maybe not. Actually, there is a more optimal solution. Doesn't really matter right now. Our topic is recursion. So how to rewrite this nice, elegant solution with recursion. First of all, what is recursion? So template will be the same because obviously we are going to feed this function with our number and we're going to expect the Fibonacci number. So the template should be the same. Recursive. So what is recursion? Recursion is a method of solving a problem where the solution depends on solution to smaller instances of the same problem. So basically we have a big problem here. What is a Fibonacci of this number? The idea is to somehow divide this big problem to a smaller problems. And by solving those easy problems, we're going to get the solution of the big problem. That's a very high level idea. What do I mean by that really? And again, this is extremely popular topic on every coding challenge. So I'll do my best to explain. Basically, in purely computer programming language, we are using recursion whenever inside the function, we're going to call the same function. So this will be, but every time we're going to call the function, we're going to call it with different arguments. with smaller problem. And by naming this smaller problem, I do not mean that the number will be smaller, maybe, but in general, the problem should be easier to resolve. Sometimes the argument will not be integer, it can be string, it can be some class, it can be Boolean, so it doesn't really mean really smaller number, smaller problem in general. Somehow, you need to somehow make the problem smaller. Okay, so let's say in general what is Fibonacci number, right? So we know that every single, let's say f from number equals f from number minus 1 plus f from number minus 2. This just logically comes from the formula, right? So Fibonacci from number is a sum of two previous Fibonaccis. What if we are going to say that if this function, whoever calls this function, wants to know what is the Fibonacci of number, what if we just return same function from number minus 1 plus same function number minus 2? Looks like magic now, I know. But let's try to understand what goes under hood if we say that. I'll just move the formula here. Let's say we have f from f, I mean this function, recursive Fibonacci. Let's say from 5. In that case, our function right now will call internally f from 4 plus f from 3. Then every single call will go to the same function again. And every single call will split the problem again. So f from 4 will be splitted to f from 3 plus f from 2. Same here, f from 3 will be splitted to f from 2 plus f from 1. Just based on this formula, because f from number is f from number minus 1 plus f from number minus 2. Should be clear, right? So that's just one line of code, basically. Now, f from 3 will be splitted to f from 2 plus f from 1. Obviously, if we are not going to stop this process, it will be infinite. So it just infinitely will split and split and split again. So recursion, one more extremely important part of recursive function is to stop the recursion. This is called base condition of recursion. The easiest problem that we know the answer right away. We don't need to calculate anything. So for example, in this case, we know that f from 1 is 1 and f from 2 is 1. This is like base condition, right? This is base of our Fibonacci sequence. So let's assume that f from 1 and f from 2 will be our base condition. We know exactly the answer right away. We will not go into recursion further. We're going to stop the recursion if we see argument as 1 or argument as 2. In that case, we will return 1 right away. So this will return 1, this will return 1, this will return 1, this will return 1, and this will return 1. The total is 1, 2, 3, 4, 5. The total will be 5. And if you will take a look on the sequence, 1, 2, 3, 4, 5. That's exactly Fibonacci number we are looking to. Does it look like magic, or you kind of understand what's going on? Can you provide plus, minus, or plus, minus in select, please? How do you feel, guys, about this? Perfect. Good. Good. Okay. Great. So let's move forward. Let me clear this. In terms of code, this looks pretty easy. If number equals 1 or number equals 2, we know the answer right away. We just return 1. That's a base condition of our base recursion. Again, this is recursive approach because we use the same function inside the function, and we do not use iterative approach. We do not iterate with the loop to calculate something. We just call the function again and again. Let's quickly validate our recursion Fibo test. And I'll just use recursive Fibonacci here and do the same test. And test passed. Perfect. Can we solve it using memorization and dynamic programming? Yes, absolutely. There is one more approach, which is called dynamic programming. I would definitely, we will not show it today because it's a completely different topic. We are showing recursion here, and let's leave dynamic programming for dynamic programming section. Now, what is the runtime complexity of this strange approach? What is the runtime complexity? Any guesses? That's actually not non-trivial at all. So I'm not even sure how to, you'll probably need to believe me in this case. I hate to do that, say something without explaining, but it's really easier to believe, because to prove the complexity here, you need to know the basic of special, I mean, there are special formulas here from algorithm theory that are needed to prove the recursion. So it's really not required on the interview. It's absolutely big plus if you know the answer. So for this case, the runtime complexity is horrible. I think the runtime complexity will be 2 to the power of n here. Why? You can kind of intuitively understand this, because every single operation is split to 2 operations. And then every next operation from those two is split to two operations again. So basically we're talking about 2 to the power of n operations in general, which is terrible runtime complexity, much worse than iterative one. So again, you never want to use this in real life, but it's just a good problem to explain the recursion, because we don't have many sequences where the recursion is in the formula itself, right? So it's just good to understand. Great. What about memory complexity? Memory is not good as well, because recursion, I think it's big offerman here, because recursion works in that way that you will go into depth into what we call stack, and every new call will be added to that stack. So basically, if you have big number here, you go inside the, you have 10. So why runtime complexity is that bad, and memory as well? Because you can, if you remember the pyramid I just drew, we have function from 3, big F from 3, from left side and from the right side. And we have to recalculate F from 3 2 times. So the approach, which is called memoization, Olga just select us, solves that problem, because we basically memorize the intermediate answers just not to repeat ourselves. We do not need to recalculate F from 3 2 times. And if you have F from 100, you calculate hundreds of times same problems. That's why this approach is not efficient at all, but it's really good to understand how recursion works. Let's do one more very similar. Let's do one more very similar, which is called factorial. Factorial. So public int factorial, int n. What is factorial? Factorial is, let's say 10 factorial is 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. So basically 10 factorial is 10 to 9 to 8 to 7 to 6 to 5 to 4 to 3 to 1 to 2 to 1. Extremely big number, by the way, right? You cannot calculate, I don't know, a couple of hundreds factorial, because it will be a huge number. Can you think of an example of a problem that is easy iteratively, but still much better recursively? You mean better in terms of efficiency, or better in terms of something else? So more efficient recursively? It's a hard question. I see what you mean. I don't have such problems on top of my head. I think that it's just, maybe some exist, but the problem is almost always, if there is iterative approach, it will be probably more efficient. The problem is there are lots of problems where iterative approach just does not exist. You cannot solve that problem iteratively, especially when we are talking about some data structures such as graphs or linked list or trees. There is just no way to iterate through them. The only way to iterate through those data structure is to use recursion. We'll definitely have some examples in the next series of this coding challenges. So yeah. But question is great, thanks. Okay, factorial. So what do we have here? What do we have here? basically we can say that f from m is f from m, sorry, is n times n minus 1 times n minus 2 times etc. times 1. So this is not recursive formula, right? Because recursive formula requires you in the right side of your equation, it should be f as well. Basically, if you are trying to explain what is factorial, you need to do it using the word factorial in order this to be recursion. So you just, this is not recursion at all, right? Again, this can be solved iteratively pretty easy, right? I will not even show it because you can just start one for loop from 1 to n and just do a product. That's it. But how to do it recursively? The answer is if you can replace some part of this right part of equation using f, using factorial. It can help. Any guesses? F from, I mean, when I write f, f means factorial. I can just say n exclamation mark will be the same. I just use the function notation. So basically, this is the same. F from n or n exclamation mark. I just say factorial of n with that. So any guesses, what can I do with this right part in order to somehow replace it? Okay, let me help you. Let me help you. Let's try to think what is factorial of n minus 1. This is n minus 1 times n minus 2 times 1, right? So f from n is n times n minus 1 times n minus 2, blah, blah, blah. F from n minus 1 is n minus 1 times n minus 2 times 1. Again, f is the same as this. I just somehow say function of this. So f from n is different from f n minus 1 is just on this n. So basically, if I will replace all this part, which is same here, with this, because if this equals this, I can just substitute this part with f n minus 1, right? So this will be correct. F from m equals n times f n minus 1. That's our recursion here. It hide it. You have to find it, basically. Please mute yourself. Let me mute everybody. Great. So now we know how to do it recursively, right? Because basically, if factorial, somebody asks us what is factorial of n, we can say it's just the same that n times factorial of n minus 1. That's it. Looks like magic, right? But it actually works because this is just a formula. We just proved it. So f from n is same as n times f from n minus 1. This is recursion because you are calling the same factorial with somehow simplifying the problem inside. The argument is smaller. So what is the base case of this? Obviously, if somebody asks us what is factorial of 1, we know that factorial of 1 is 1. That's our secret. That's it. Let's try to do some unit testing. So let's say factorial from 5. Factorial from 5 is 120, right? 5 times 4 times 3 times 2, 120. So expected result is 120, and the actual result is this. So let's do some testing. And test passed. By the way, if you're going to try to use factorial from 100, your mark will just stuck. Actual result is 0 because I think it just so basically it's I think computer cannot count factorial from 100 because factorial from 100 is some huge number with 157 zeros in the end. I just googled it. So never try to do it. Factorial from 5 is fine. Cool. Now let's do the last recursion problem. Last recursion problem. We are given with some number. This is natural number. Natural is a positive whole number. Yes, int definitely does not support that many chars in the number. Modern int supports what? 32 bits, I would say, right? Or 64? Yeah, 32. Int is 32 bits. So the maximum number there is 2 billion. 2 billion with something. Feel free to Google why. It is important to understand as well. It's how actually the computer built in binary system. Cool. So what's our, what about runtime complexity? Same, it's not that trivial to really calculate it and prove it. So I would not show this during the class. Feel free to Google and to check it out if you are interested to how to prove it. There is some formula that will help you, but you can intuitively say that every single call leads to another call, to only one call, right? So roughly this will be n calls. If we have 10, this will be 10 times factorial from 9, that will be 9 times factorial from 8, etc., etc. So roughly this should be around big O from n, because we have just one recursion call here. And here we have 2 recursion calls, so everyone is splitted, which is much worse. Yes, so this is big O from n, and memory is same big O from n. Just to memorize or Google and understand why. There are some articles in the internet that will explain you how to prove it. Great. By how much can we decrease complexity if we use memoization? So the memoization approach will probably, let me think, what will be the runtime complexity there. It should be, so basically we'll remember. So we will definitely have worse memory complexity with memorization than iterative approach, because iterative has we go from one, and memorization will definitely store some variables like array or dictionary or whatever. But I don't really, I need to think about it. Feel free to write the memorization approach and try to Slack me or in the channel what is the result there, and we can discuss in Slack. I cannot say it without seeing the code. I need to write it actually, but should be a rapid increase, because basically those methods are just terrible in terms of runtime, just terrible. Okay, so the last one, public int sum of digits. So basically we have number, which is natural number. This is by default. And you are asked to count the sum of digits in this number. We know already how to, we did something similar when we did integer palindrome, but now we need to do it with the recursion. How to do that? Remember this division by 10, magic division by 10, this will help us. So we can say that reminder is n times modulo divided by 10. So if we have some number, this guy will give us 4. So modulo division by 10 always give you the last number, because this is just reminder of this number, because if you divide by 10, you just can insert dot here. So this will be your reminder. So definitely this will be 4. Now, what is actual recursion step? By the way, this is called recursion step. So how to, that's a good example. We need to decrease to make the problem smaller, right? But that doesn't mean that we just need to decrement argument always, as we did here. No, for example, here, to make the problem smaller means cut off the digit, right? And leave the number with first, in this case, 4 digits without 4, right? That's a cut, that will be our cutoff. So return reminder plus sum of digits from what? How to get this 4 first digits out of 5. Just using this, the whole numbers division. N times 10 divided by 10. That's it. So to count the whole sum, we're going to get every time the reminder and add the reminder to the recursion step from smaller number. That's it. What will be our base case? So base case, the easy problem that we can return some result right away. Question to you guys. What's the base step here? Exactly. If we have 1 digit, means n less than 10. This is just 1 digit, right? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. If that's the case, we can return this digit right away, right? That's our sum of digit. Sum of digit of 1 digit is just the digit. Cool. So sum of digits. if we have sorry guys, I lost my network because of electricity. So let's quickly finish with hopefully the recording will not be splitted into the two parts. Okay, so let's say we're interested in 1, 2, 3, 4, 5. So 12,345. And we know that the expected result is 5 plus 4 is 9, 10, 15. Great. So if we are going to say sum of digits from number, we should get 15. Let's run it. And test passed. Great. What else? We should probably think on front-end complexity here. I'm not really sure what is that without calculating. Actually, no, we can say. So every time you divide by 10, so basically this will be definitely a logarithm of 10 of this number. So time here will be something like big O. Big O from log, like LG from N, I think like that. Need to double check that actually. Yeah, I think this should be right. Anyway, if somebody has any other, yes, a log with base 10. This is a log with base 10. Not natural. I mean, this is just roughly runtime complexity. Obviously, it's not the exact number of operations. Anyway, every single runtime complexity estimation is estimation. But yes, this is a log of 10 because every time we divide by 10, so how many times we will be able to divide this by 10? Exactly the log with base 10 from n. Yes. Actually, the memory is even a bit harder. I think the memory is same because this will be exactly how many call size in stack do we have. Again, all those recursion estimation, especially memory, is harder than just estimation as we did in all our previous algorithms. So ideally, you should be able to count this using formulas. Otherwise, you just need to roughly be able to estimate, kinda intuitively understanding the number of times this will be executed. So this will definitely be executed how many times? The exact number of times we can divide this by 10. We can divide this by 10. 1, 2, 3, 4, 5 times. So overall, roughly 5 times, 5 operations, and we're done here. That's basically it for basic recursion. So we did Fibo, we did Factorial, and we did sum of digits. Thank you, guys. Feel free to practice recursion and see you next week.